Or you're in Australia?
Yes, I am.
How are you?
It's good here. The COVID situation is under control here.
Okay.
Yeah.
Good.
How are you guys in Shanghai?
Yes, everything's getting normal.
Mhm. Yeah, I think the vaccines are starting to be done in Australia.
Did you get the vaccine?
Not yet. I think maybe in a couple of months or something like that.
Couple of months. Okay.
Yeah. Let me just try to mute my iPad. I'm not sure why it's not muting.
Oh, I think it's time.
Okay.
Are you ready?
Yeah.
Okay. Hello, everybody. It's my great pleasure to have our today's speaker, Dr. Guo Hao from Texas A&M, who is actually now staying in Australia. He will talk about the scalar curvature, bandwidth, and quantitative K theory. Let's welcome.
Okay, thank you, Professor Wang, for the introduction. Thank you for the invitation to speak at this great seminar. So today I'm talking about two connections between scalar curvature and K theory, which come from the quantitative way of looking at K theory. So the first connection is a quantitative version or quantitative refinement of chi index, and also Lishnerovit's vanishing theorem in this framework. And the second connection is a quantitative approach to Gromov's bandwidth conjecture, which has been recently studied by Zeidler and Cecchini. So we'll give a quantitative viewpoint on this. So this is joint work with Zhijiang Xie and Guoliang Yu at Texas A&M. And so first I'm going to start by just recalling the construction of the higher index and how it relates to PSC. So let N be a manifold, which is spin. We have a Riemannian metric G on the manifold, and we have a Dirac operator on L2 of the spinors. I'm going to use the row algebra, which is denoted by C star of M. That is here. And also its multiplier algebra. So the row algebra consists of essentially the locally compact operators on L2 with finite propagation. So here, locally compact just means that if you have a function f which is compactly supported, so that should be a function, not a section. compact explorer function and you compose it on the left or the right with your operator t, you get back a compact operator. And finite propagation just means that given some section which is supported on some compact neighborhood, it gets translated only up to a distance r away for some finite r, independent of the section you started with. And if you take the infimum of, oh, someone's texted me. If you take the infimum of all these r, you get the propagation of the operator. So that's the finite propagation and locally compact. And after taking closure inside the bounded operators on L2, that's the Rowe algebra. So to construct the index of the operator, notice that we have a non-compact manifold in general. So it doesn't make sense to talk about the Fredholm index, but it does make sense in this type of framework. We take a normalizing function chi, which is an odd function, it's continuous and goes to 1 at infinity. So it looks something like this. And we can use function calculus and form chi of d, and that's a bounded operator living inside the multiplier algebra of the Rowe algebra. And it satisfies its condition that chi squared of d minus 1 is actually in the Rowe algebra, because chi squared minus 1 is a C0 function on the reals. And so because of this property, chi of d is invertible. And so we get a class, which is the class of chi of d in this quotient, and it represents a class in K1. So now we have an inclusion map of the Rowe algebra into its multiplier algebra, and again, a projection into the quotient of the multiplier divided by the Rowe algebra. And from this short exact sequence, we get a 6-term exact sequence in K theory. The higher index of d on this manifold M is defined to be the boundary map of that sequence applied to chi of d. So here we get something in K0 because we're dealing with dimension of n being even. So I'm going to be using an explicit representative for this index. So to get this, let's set L to be equal to 1 minus chi squared. So then the index can be represented as the following 2x2 matrix. So it's basically L squared, L times chi of d, and some other expressions. But you notice that this expression has a factor of L in every entry. And this is not quite correct because in our situation, we have a grading on chi of d, but up to grading, this is correct. And this can also be written as a difference of idempotency in 2x2 matrices with values in the unitization of the Rowe algebra. So now if the scalar curvature is positive everywhere on M uniformly, so it's bounded away from 0, then we have the Lishnarovitz formula, which is d squared equals nabla star nabla plus kappa on 4, where nabla is the connection on the spinors. So therefore d is invertible and it's got a spectral gap. So here I've tried to show the spectral gap. It's from minus square root of c on 2 to square root of c on 2. So therefore we have a continuous function, the sine function is continuous, and we can form the functional calculus again. And this has the property that 1 minus chi squared is exactly 0. And from the formula for the index representative, we see that the index vanishes. It's actually exactly 0. So therefore, in this kind of framework, uniform scalar curvature leads to 0 index. So non-vanishing of the index is an obstruction to positive scalar curvature of this sort. So the first thing I want to do is talk about this in the framework of quantitative K theory. So we'll see that this vanishing theorem sits naturally inside the quantitative K theory. So now the first thing to notice is that C star M, the Rowe algebra, is actually geometric in the sense of it's got a filtration, which is indexed by R, the propagation of operators. Right, so the algebraic part of the Rowe algebra can be broken down further into this CMR, which is operators with a propagation at most R. And then the Rowe algebra will just be the closure of the union overall R of these pieces. So these are vector spaces. And quantitative K theory is the theory that refines operator K theory by taking advantage of this kind of structure. And for references, I'll quote Guo Hao's paper, where he initiated this kind of study, and also a Yuno and Yu's paper in Annals Institute Fourier. So to define quantitative K theory, so let's again look at just the even case. So say we have a C-star algebra. We could either use quasi-projections and quasi-unitaries or quasi-idempotents and quasi-invertibles. Both are fine, but because in this talk we'll deal with the index idempotent, we'll take the second approach using idempotents and invertibles. So that's just a remark. So to do this, let's fix some constants. So epsilon is going to be a small number between 0 and say 1 and 20, some small number which will keep fixed throughout this talk. N is going to be sufficiently large, let's just say 7. You'll see why, because the index idempotent has a norm of around 7. And then R is some constant, which will be the propagation of operators. So that's going to be the filtration. So an element in C star M unitized is called an epsilon Rn quasi-idempotent if essentially it's idempotent up to epsilon, it's propagation R, or at most R, and the norm of itself and 1 minus E is at most N. So that's a quasi-idempotent. And similarly, you can define for matrix algebras with entries in this algebra what it means to have propagation. The propagation would just be the supremum of the propagations of the entries. So we have entries, we have inclusions of these matrix algebras or idempotents in them into idempotents in bigger matrix algebras, just by taking a quasi-idempotent and putting it into the left top corner of the bigger matrix. Right? So in this way, we can collect together all of these quasi-idempotents over all sizes of matrices, and we get a set, and we can say that for two elements E and F, they're homotopic or they're equivalent if there's a homotopy connecting them through 4 epsilon R, 4n quasi-idempotents. So the reason for this additional 4 is that we want a bit more room to work with when we do this equivalence relation. And the result is that if you take this equivalence relation on the set of all these quasi-idempotents, you get a monoid, and the monoid is given by addition of matrices in the usual sense of K theory. So taking the growth and decompletion of the monoid gives you the quantitative K group, which I'll write as K, so K0 in this case, epsilon Rn of the algebra. So here it's unitized, but we can get rid of the unitization by looking at the projection map from the unitization to C, and the map induced at K theory level, and take the kernel of the map. And the kernel of that map is going to be K0 of the ununitized Fourier algebra. So as a remark, so all of this stuff can be done whenever you have a filtered or geometric C-star algebra. It doesn't have to be the Rohr algebra, but here we're just going to be specific and look at the Rohr algebra, but it works in general. So some important facts about these groups. So the first thing is that these groups approximate operator K theory of the C-star algebra in question. And it does this as R and N go to infinity. So that's the first important thing. As the propagation goes to infinity, you get back the usual K theory. The second thing is that as R goes to 0, things localize. You're looking at small propagations. So as R goes to 0, we get back the K homology in this case of the manifold. And so this parameter R kind of interpolates between K homology and K theory in this way. And as R goes to infinity, it becomes less localized. So there's a controlled cutting and pasting procedure for these quantitative K groups, which makes them more computable. So that was the original reason for introducing these groups. So here's an example. So let's take M to be the two-sphere. Then K-homology of the two-sphere is Z plus Z generated by the Dirac operator on S2, and Dirac operator tensored with the bundle. And so that's when R is sort of 0. And as R goes to infinity, what you get back is operator K theory of the row algebra on S2. Because S2 is compact, C star of S2 is just a compact operators on L2. So that's going to be Z K theoretically. So R is kind of interpolating between these two things. So the higher index is compatible with quantitative K theory in the following sense. In the sense that if we take a normalizing function that we can use to define the index, but we take it so that the Fourier transform of this function is compactly supported, then chi of d actually has finite propagation. So this is because we can write chi of d as an integral like this. So it's an integral of the reals of chi hat of t e to the itd. So that's the wave operator defined by d. So because the wave operator has finite propagation, and this thing has finite support, so you get something which has finite propagation. So if you look back at the index representative in terms of the matrix, this means that this representative will be also finite propagation. So it's a difference of idempotents, both of which are finite propagation. So therefore, you get a representative for the index, which is living in one of these quantitative K groups for finite R. So that's what we call the quantitative higher index. It's index represented by one of these finite propagation representatives living inside quantitative K theory. And you can show that it's independent of the choice of appropriate chi. So if you had another chi which was valid in this sense, they are homotopic in the sense of quantitative K theory. So that's the definition of this quantitative refinement of the higher index. The vanishing theorem of Wisniewicz also refines in this sense. So to see why this is, suppose that we have positive scalar curvature everywhere, right? So kappa bigger than equal to c, bigger than 0. Then I claim that for any r, for any propagation r, if the c is sufficiently large, then the index is going to vanish. So the index at scale epsilon rn is going to vanish quantitatively. So to see why this is, so let's define delta c to be the supremum of the difference between the sine function and our normalizing function outside of the spectral gap. So on the part where it's interesting. So if the spectral gap is here, then delta c would be something like this difference here. So now the index representative has a factor of L. So it factors as L times B for some matrix B. And L again is 1 minus chi squared. So by construction, the size of 1 minus chi squared is small whenever delta is, right? If delta c is small, then 1 minus chi squared is small. So the larger c is, the smaller delta c becomes. Because the larger c is you're moving to the right-hand side here and you're moving to the left-hand side here, so delta is going to shrink. So therefore, for sufficiently large c, L times B, this quantity is going to be very small in norm. And here's a fact: if you have a quasi-idempotent which is very close to 0, sufficiently close to 0, then this is actually 0 in quantitative K theory. So you can make this precise, again, by the references that I quoted earlier. So this means that if we begin with some R, we can choose C to be large enough compared to R that the index vanishes at the scale R. So similarly, if you have any C, you can choose R to be sufficiently large, and the same thing will happen. So the proof for this is, well, let's take our finite propagation representative, so chi, which is a normalizing function with Fourier transform compactly supported. Let's scale chi by a parameter t. So chi sub t of s is chi of Ts. So as t goes to infinity, so if this is chi, as t goes to infinity, it has the effect of squeezing chi into a sort of smaller towards the center. So as a result, you see that delta c is becoming smaller and smaller at the fixed c, right? As t goes to infinity. So, but because delta t is going to infinity, delta is going to 0, by the same logic as before, the norm of this quasi-idempotent becomes very small. So the index vanishes in quantitative K theory. So these kinds of two things are related to each other. So notice so far we haven't actually used anything about the manifold itself. We've just used some basic functional analytic arguments involving one particular choice of normalizing function. So what we obtain is a quantitative K-theoretic abstraction to positive scalar curvature, but it involves the size of the scalar curvature. It's not just the positivity, but it's the size. So here's the theorem, which you can easily write down after thinking about this. So if you fix epsilon and n as before, say we have kappa bigger than equal to c, bigger than 0 everywhere on the manifold, then the index is going to be 0. The quantitative index will be 0 for all r large enough. And large enough means it's proportionally, it's inversely proportional to the square root of c with some constant omega 0. And omega 0 is independent of n. Yeah. So square root of c appears here because square root of c appears also on the graph. So they're inversely proportional. And I'll just say that so far this is in a setting of a non-compact manifold with row algebra, but this also works, for example, in the equivariant setting where you have a group action on the manifold, and you can think about the equivariant row algebra. Also in the maximal setting. So if you take the maximal completion of the algebraic row algebra, whenever that exists, then you can define the maximal coarse index or higher index. And everything here will go through for the same reason. So in some sense, this is a refinement of the usual obstruction. The usual obstruction says if you have uniform positive scalar curvature, then the index vanishes. But this says if you have scalar curvature above a certain level, then not only does it vanish at scale infinity, it vanishes at some finite scale, which is proportional to how large the scalar curvature is. So if we continue the example from before, m equals S2, so this has positive scalar curvature, then remember that R interpolates between the K homology and the K theory, and K homology is 2 copies of Z, and K theory is 1 copy. So at some R, this goes from being 2 copies of Z to 1 copy of Z, and the thing that vanishes is the index of the Dirac operator on S2. So that copy vanishes. So it's interesting to say, ask, when does this happen? At what scale does this happen? Okay, so the second thing that I wanted to talk about was an approach to the bandwidth conjecture of Gromov using tools from this type of discussion. So first, let me just recall, the bandwidth conjecture says that suppose you have a closed manifold of dimension n-1, and n-1 we assume to be bigger than or equal to 5, which does not admit a PSE metric. Then there is a universal constant Cn, so depending on the dimension, such that the following thing happens. So for any Riemannian manifold V, diffeomorphic to n cross the closed interval -1, 1. So this is called a band, such that V has positive scalar curvature. Then the width of V is confined by Cn divided by square root of sigma. So here I'm using sigma because it's a second part of the talk, but it's, you can think of it as C from the same, in the same notation before. So the width here is defined to be the distance between the two ends. So delta minus and delta plus, which is n cross plus -1. And the distance is the Riemannian distance induced by the metric. So basically this says that if the length of the band is too long, right, then the index has to vanish. Or in the spin case, that's what it says. So Zeidler and Cecchini prove this in the case when M is spin and with non-vanishing Rosenberg index. So in the case of spin, that's where you use a condition that M does not admit a PSC metric. And they did this using Callias type operators. So these operators which are Dirac type plus an endomorphism. And they actually obtained the sharp constant Cn equals 2 pi times the square root of n minus 1 on n. So this is sharp by an argument of Gromov, and it actually holds with strict inequality. So this inequality here is actually strict with that optimal constant. So what I want to do is to talk about this problem in the context of this quantitative K theory or tools from quantitative K theory. And I'll give an approach that shows that a constant Cn exists. Right? It may not be the optimal one, but such a constant exists. So what we show is the following. So this is a theorem that I like to outline. So suppose M is closed, n minus 1 dimensional spin manifold, and we take the fundamental group of M to be gamma. So it's supposed to have a Dirac operator, which is the lift of the Dirac operator on M to the universal cover M tilde. Then if the length of the band is, so the length of the band is defined as before, is bigger than C times the square root of n minus 1 divided by n times 1 on square root of sigma, where C is some universal constant, then the index, so in this case, it's the equivariant maximal index of dm tilde equals 0. And this is an index that lives in the K theory of the maximal group C star algebra. So a couple of remarks about this. We can replace this kind of maximal index by the reduced index or something like that. It applies, the same argument applies. We also get an explicit bound for what C is, even though it's not as good as the optimal constant, but it's a constant that is finite. And you can also refine this by choosing the correct functions, as I'll say a bit more later on. And so yeah, it's maximal higher index. So here's a sketch of the proof. So suppose you have V equals M cross minus 1, 1, and you have a Riemannian metric GV on this band with scalar curvature bounded below by sigma. Let's define V tilde to be M tilde cross minus 1, 1, universal cover, and G tilde V to be the lift of V to this this band with a gamma action. So we'll notice that the width of this band is the same as the width of the band we started with because of the gamma action. So we can embed this new band into M tilde cross R, so just a cylinder in a natural way. So I'm going to use this picture here. So D tilde minus is the left end cap and D tilde plus is the right end cap. You've got 0 here. So all the distances are not reflected in this coordinate system, of course. We have some Riemannian metric. So the first thing is let's extend this metric on V tilde to all of the cylinder. And we can do this in a way so that it's a product metric outside of some compact neighborhood of V tilde. Right? So we can just homotop it to a product metric outside some neighborhood. And amongst other things, this ensures that the maximal higher index exists. Right? The geometry is nice enough for this index to exist. So let D be the associated distance function. And while I'll write D sub this kind of del tilde minus to be the sign distance function from one of the end caps, the left end cap. So it's minus on this side, is plus on this side, and the distance between this end cap and this end cap is exactly R. So here's just some notation, some fairly obvious things. So M tilde plus is, if you look at this diagram, it's this portion, the yellow portion. M tilde minus, sorry, it's the other way. M tilde plus is the green portion, M tilde minus is the yellow portion. And in the middle, M tilde 0 is the intersection of these two bits. So The reason for introducing this is because we want to work with distances now, not with just the coordinate 0 and -1, 1. So after smoothing the distance function a little bit, we can assume that L log 2 is a regular value of this function. And so therefore, m tilde 0 is a nice manifold. So we have a decomposition of the cylinder into two parts. One part is m plus, one part is m minus, and they glue together in the middle by m0. So from this is actually a coarse decomposition. And from this, you get a coarse Maya-Viatora sequence. And the connecting map of this Maya-Viatora sequence goes from Kn of the Rohr algebra of the cylinder, equivariant Rohr algebra, to Kn-1 of the Rohr algebra on the middle bit. And because m tilde 0 is a gamma co-compact manifold, the Rohr algebra is Morita equivalent to C star max of gamma. So this is the K theory of C star max. So a version of Rohr's partition manifold theorem tells you that if you take the boundary map applied to the index on the big manifold, you get the index on the middle piece on the cross section. Okay, so again, for uniformity, let's suppose that n is even dimensional, right? N is even. Then the left-hand side can be written in an explicit way, in the following way. So suppose that we've got index of the Dirac operator on the cylinder, represented by some matrix A chi, right? So going back to all the way back to the matrix A chi from here. It's just some choice of normalizing function applied to D. So if we represent it like this, then yeah, so we're choosing some representative, and let's form A chi plus to be the restriction of this guy to the positive half of the cylinder. So it's explicitly it's A chi times the characteristic function on the positive half of the cylinder. Then A chi plus is a difference of idempotence in the quotient of the 2x2 matrices of the Rohr algebra on cylinder divided by 2x2 matrices on the Rohr algebra of the middle part. So this you can verify. And explicitly, you can write the boundary map applied to the index as the exponential of A chi plus of this restricted index idempotent. So that's an explicit expression for this Maya-Viatora map. So now here's a remark. So if A chi plus were actually a difference of idempotence, or say an idempotent in the big algebra without dividing out, then this of course vanishes after exponentiation. So the idea is here we want to show that if sigma is sufficiently large, then this happens up to epsilon. So in other words, A chi plus will be a difference of quasi-idempotence. And if it's close enough to be an idempotent, then after exponentiation, you still get 0. So that's how we can show index vanishing. So how do we do this? So recall that if the scalar curvature is bigger than sigma everywhere on the cylinder, which we don't have, but if it were the case, then the d square would be positive and have a spectral gap. So the norm of any function applied to d would be bounded by the spectral theoretic thing here. But because we only have kappa bigger than sigma on V tilde, not on the whole cylinder, we have the following lemma by Rohr. So this lemma says that if you have a section which is supported inside V tilde, inside the part with positive scalar curvature, then the norm of your operator f of d on this part of the manifold is exactly the same as what you would expect here. So the caveat is two things. So the caveat is that phi first has to be supported inside of this thing. So it's not quite just on V itself, it's away from the boundary of V a little bit. And the second thing is that for this to happen, f has to have compactly supported Fourier transform. But provided these two things are satisfied, you get this kind of estimate. So here's a picture. So we have our cylinder, we have the two end caps. If you have something supported away from the end caps, then this is where the estimate applies. So if sigma is very large, then chi applied to d squared minus 1 is very small on this part with positive scalar curvature, right, by this lemma. For the same reason as before, because chi is now very close to the sine function outside of the spectral gap. And because the index representative a chi has got a factor which is exactly this chi squared minus 1, it's actually very close to 0. So now here's the claim. If you take the propagation of chi to be small enough, the small enough turns out to be less than or equal to L on 3. If you take it to be small enough, then we can ensure that the restriction process of restricting the index representative to the positive half doesn't completely destroy the idempotence property. Or more precisely, it doesn't completely destroy the property that a chi has, which is being a difference of two idempotents. So it's still true up to epsilon. So the reason for this is because, okay, if we look at the cylinder in 3 pieces, we have part A, part B, which are separated by some distance. And in the middle, we have something which is very close to 0 by this fact here, right? So now if you choose the propagation to be small enough, so less than ln 3, say, that means part A doesn't interact with part B. So a chi restricted to part A doesn't interact with a chi restricted to part B. And in the middle, it's very close to 0, and the 0 operator has 0 propagation. So in other words, up to some epsilon, determined by how small this middle part is, a chi is basically a 2x2. It's a graded thing. It's a direct sum of a chi plus and a chi minus. Right? So the multiplicative behavior carries over from a chi to a chi plus. But we know that a chi is a difference of idempotence. So therefore, a chi plus is also a difference of idempotence up to some epsilon. And so that means if sigma is sufficiently large, then the length, some fixed length between these two end caps. If you take the, if you exponentiate a chi plus, you're going to get something which is 0, which is 0 because it's a quasi-idempotent. So that shows that for sigma sufficiently large, yeah, the index vanishes, and we know that this index on the cylinder is exactly the same as the index on the middle cross section. So we're getting vanishing of the index, and that proves the theorem and shows that there exists some constant for which this is true. So if you go back to the calculation, it depends heavily on the choice of chi, how good an estimate we're going to get. But any chi is sufficient to already show that there is a constant, right? But one can try to refine what chi is to get a better estimate. So in the paper, we actually give some precise estimate for when this is, for how big the constant is, how small we can make it, but we don't get the optimal constant. But it's possible to try to choose a better normalizing function so that the estimate improves. And I'll say that, yeah, this also works in the odd dimensional case with quasi-unitaries instead of quasi-projections, and that's also discussed in the paper. Yeah, but the basic idea is here that L and square root of sigma must be inversely proportional, and this relationship is similar to the relationship in the first part of the talk about the vanishing, the scale at which the index vanishes. Okay, so I think for some reason I've gone through the whole talk very quickly, but this is all I prepared, so I think I'll end here.
Okay, we have plenty of time. Any questions? To Hao.
Well, there is something which you might think of using,
Yeah.
which has been found by engineers, I mean, by Slepian and other people, I mean, and it's a great thing. It's called band limited functions on the, so if you want, the origin of this discovery was the problem of information transmission. And so these people were looking for functions which do not exist, which have compact support in time and compact support in frequencies. Of course, such functions do not exist, we know very well, because if you take the Fourier transform of a function with compact support, it's analytic, so it cannot have compact support. However, they found functions which are which are the best with respect to this problem. And I mean, this can be understood at the mathematical level, because what you have two idempotents. You have the idempotent of projection on the support in time, and you have the projection on support in Fourier. Now, when you have two projections, you have a representation of the diagonal group, and this means that the irreducible situation is of two dimensions. So when you have two projections, they are characterized by an operator, which is an angle, and which has eigenvalues and eigenfunctions. And these people, Pollack and Slepian, many years ago, found that the eigenfunctions for these two projections can be computed because they fulfill a differential equation, which is called the Prolate differential equation. Now, it seems to me that when you were trying to optimize the choice of the function, it could be interesting to relate to this situation, because you were trying to optimize, you know, in pretty much, and there is something which is a principle which comes from quantum mechanics, but which they push to the extreme, which is precisely that the product of the two widths is bounded below because of the uncertainty principle. But what they have found is much finer than that, because so I mean, so this is purely, of course, on the choice of the function that you take. I mean, but as far as I understood from your talk, I mean, much is going on at that level.
Yeah. I see. So, that's very interesting. Thanks.
Yes, I mean, it is some work which I have used already in existing papers, but which is very beautiful, and which, if you want, what is amazing is that one would never believe that the characteristic function of an interval would actually commute with a differential operator, but this is the case.
Right.
So, for instance, if you take the characteristic function of the interval -1, 1, it commutes with the differential operator, which is d by dx times 1 minus x squared times d by dx. So I mean, these things are known, but I think they are worth looking at. I mean,
right.
Okay.
Yeah, thank you.
Any other questions from audience?
Could I get the name of the authors of the paper? I think the one that Alan just mentioned.
Okay, so let me give you a precise reference. Yes, so you can see the paper which I like the most is by David Slepian, S-L-E-P-I-A-N, and it's called Some Comments on Fourier Analysis, Uncertainty and Modeling.
I see.
It is in the Siam Review, volume 25, number 1, and it's July 1983.
Okay, great, thank you.
Yeah.
Are there any more questions? Comments? Is it possible to use the localization algebra to deal with this, all these situations?
To do with positive scalar curvature?
Yes, do the similar things. Did you talk about that?
I haven't thought about it, but I guess it's possible, but I haven't thought about this a lot.
Since the localization algebra usually can do the almost similar similar job.
Yeah.
I'm not sure.
Yeah, that's an interesting idea.